Today we have a hard problem. Given some binary string, we want to find for each query of the positions what is the maximum possible ones we can have. For example, query from 2 to 4. This is a range, and we find the maximum connections of two islands of zeros that we flip to ones, and then we count how many ones we have total. Okay, I didn't solve this problem, and I try to explain what I understood from my solution after I finally got it. Like, my solution is binary indexed tree. Okay, we first can sort the queries by its bottom right border, and then we can walk the string in a single iteration, and for each position we assume we have right query at most current position. So for example, this is I, current position, and we calculate all the queries that have the same right border. Okay, this is one step. The second step is how we calculate these islands. We only care about the current one. This is current length, and previous. This is previous length and previous start. P start. And we want to store some information about this configuration to make sure we can query this entire prefix for every L position that we can have in the queries. And we can use binary indexed tree and store the information like this. For each binary indexed tree of L position on the left, we store the length, equal length of zeros we could have that could be converted to ones. So basically, for this example, 0, 1, 2, 3, 4, we have p start equal 1 and p length, previous length, equal 2 and current length equal 1, and we store in the binary indexed tree, we update for position p start 1, we update the possible conversion from 0 to 1. It is p len 2 plus p current len 1. It is 2 plus 1 basically equal 3. This is update operation. And then to actually do the query operation is just a query of binary indexed tree of L, and it would return the maximum, max L. So binary indexed tree have one indexed, like 1, 2, 4, 8 is the roots. Then we go 3, go 6, 5, 7, And this is binary representations of 0, 0, 1, 0. This is 0, 1, 0. This is 1, 0, 0, and this is 1, 0, 0, 0 for the roots, and this is 1, 0, 0, 1, 1. This is so this is 6 is 2 plus 4. It is 1, 1, 0. 5 is 2 plus 3. It is 1, 1, 0, 1, and 7 is 3 ones. And we if we do update operation, update of to place at position 1, we put the value 3, value in index, we go and we do like idx equal 1 plus 1 equal 2, start from this, and we put value into 3, so value would be 3. Then we go to the suffix x equal and equal dx. Oh, sorry, this is a minus equal dx and minus dx. Basically, we're removing this 1, and we're going to straight to the 0. So the 2 is the final leaf. We don't actually go anywhere. Okay, and this is how it works. However, this solution is only partly works because the binary index tree skips exactly for this reason of 2 being the leaf. We can't, for example, query 2. If we put update position 1, we want to query left equal 2, like this one. This would be left equal 2, and we would just start with idx equal 2 plus 1 equal 3. This is 3. And then we going to the suffix, we doing plus 0, 0, 1, and it goes straight to 4, and then it goes straight to 8, and all of them are zeros. Basically, we skipped this 2. The binary indexed tree answers the question for this left position or later, what is the maximum of this zeros sum. And if we happens to be placed on the left part, like 2, it skips what we had before, like 1. So we have to introduce some corner case just to this left prefix zeros that we could have, and we could have skipped them. And for this we want, or we have to introduce this for each position. We want count zeros for this each position. That's 1, plus 2, and find the next 0 group. Like for this one, next would be this one. Okay, and after that, when we computing the left, we have to manually calculate this first possible combination and compare it with binary index at 3, because binary index at 3 can go forward and look for the max here, but we have to manually compute the first binary index at 3, could skip it. Let's look at the solution. This is solution. We have let me show the minified version. This is two verbs. So this is a minified one. Okay, and this is to up, and Q is a binary index at 3 query. We start with I plus 1 and we do x minus 4. Go and update. And for query we do x plus. And this is not standard binary index at 3, because standard is for prefixes and this is for suffixes. And this is a corner case calculation of the number of zeros and jump table for the next group. And instead of sorting by query by its right border, we can just group them by its right border. And when we iterating for in the string, we can just query these groups one by one. Okay, and while we going on the string, we track how many we have current zeros and how many we track the previous start position with current zeros and I. And the length, we basically track in two groups, current and the previous one. And if we have previous, we updating the binary index at 3 with previous group start points to the current previous length plus current length, so basically total length. Okay, and for each query we only care about this left because the right is already I. And then we go on, and this is the first group of zeros. And if we happen to have a left point to this first group of zeros, we have to jump to the next group of zeros. This basically skips all the ones if we have them. And then we asking if we jumped before our right, we have to compare that this is zeros in this group, and this is a total length of this range in the query, basically taking minimum to not overshoot. And then we use this zeros on the second group, and again suffix on the range to not overshoot. And this is just the first candidate, and we compare this first candidate with what the binary index at 3 actually answers, because binary index at 3 can and would skip the first exactly. Okay, this is it for today.